Okay, so let's take a look at another example. We have a general equation written here, a plus b producing c and d, same equation we've seen previously. We can write the rate law expression for that. So the rate is equal to the rate constant k times the concentration of a raised to a certain power x times the concentration of b raised to a certain power y. Notice again, we don't see any of the products in our rate law expression. All right, so we have a set of experimental data we're going to use to determine the values for x and y. So if I want to determine, for example, how the value for x, in this case, I can select two experiments where the values for a, because that's what x is associated with the value for a changes. So I can select experiments 1 and 2. So here we see that a is doubled, b is constant. Okay, so we're not changing b. And as a is doubled, what happens to the rate of the reaction? Well, you can see, and you can do the calculation yourself. Okay, so as a doubles, the rate doubles as well. Okay, so that's a directly proportional relationship. We can say that the rate is directly proportional to a raised to the power of 1, right, or directly proportional to the concentration of a. So that means then that the value for x in our expression here is going to be 1. It is first order with respect to a. First order with respect to a. Similarly now for the value for y, and y is associated with concentration of B. So I can select two equations or two experiments where the concentration of B changes. So I can select experiments 1 and 3. And in those same two experiments, the concentration of A is unchanged. So what we can see here, if I compare experiments 1 and 3, okay, so the concentration of B is increased by 2, so it's doubled. So we can see it as B doubles, as the concentration of B doubles, what happens to the rate in those reactions as well? Well, we divide the rate of experiment 3 by the rate of experiment 1, we have down here, we see that the rate actually quadruples. It doesn't double, it actually quadruples. So what that means, okay, is that the rate is actually proportional to the concentration of B, not to the power of 1, but to B squared, right? The concentration of B, or proportional to the concentration of B to the second power, proportional to. Right, so what this means then is that the reaction is, has y here equals 2, so we can say it's second order with respect to B, and it was first order with respect to A, as we saw previously. So when we insert both of those now into our rate law expression, we can say that the rate is equal to K, right, A to the X times B to the Y. We know what that X is 1 now. First order with respect to A, and then the second order with respect to B. Okay, and what this means then is that the reaction is, we add them all together now. Remember, the 1 is understood, you can put it in if you want, but you don't need to. It's third order overall. Okay, that's how we use the terminology to express the different parts of the rate law expression, how we can calculate the values for X and Y. What we can also do, once we have the rate law expression written and we have the values for X and Y calculated, we can now use any of the data points from the expression, from the rate, I'm sorry, from the experiment to determine the value of K, the rate constant. So for example, in the one that we did previously, Okay, so we know that the rate is equal to K times A to the first power times B to the second power. That's a K here. So if I want to solve this for K, rearrange our equation, that would be equal to the rate divided by A to the first power times B to the second power. What I can do now is I can substitute those values from any of the three experiments in order to solve for K. So for example, if I wanted to, I can substitute the values from experiment 1. Okay, then my K there would be equal to the rate from experiment 1 is 2.1 times 10 to the -4. Let me highlight these up here so we know which one we're using. 2.1 times 10 to the -4, and then that's molar per second. So that's the rate divided by concentration of A. So that's 0.10 molar, and that's the first power. And then we have the concentration of B, 0.015. And then that's molar, and that's squared. Right? So if we substitute those now into, and we plug them into our calculator, we end up with K being equal to 9.3. And then our unit here will end up being molar to the -2 times second to the -1. Right? So we can determine the value for K, the rate constant, once we have the rate law expression written out, the value for the exponents, and we can substitute any values from any of the experiments in order to do this. So what you'll see is that the value for the rate constant, and specifically the units for the rate constant, actually depend on the overall order of the reaction. So here, the overall order of the reaction is third order, and if we see for a third order reaction, the units, as we just confirmed, are molar to the -3 times second to the -1. So that's something to keep in mind when we do these calculations. A few things, 3 important things to note about that rate law that we mentioned at the beginning, but you always want to keep in mind. Okay, so we said that those exponents in the rate law, you have to determine those experimentally, right? You cannot use, they're not, there's no relationship between the exponents and the coefficients, the balanced equation, right? You have to actually go through the math and solve, use the experimental data to solve for the exponents. And in order to do that, we can compare the changes in individual reactant concentrations with the changes in the rate. Okay, so changes in reactant concentrations with the rate shows how the rate actually depends on each of those reactant concentrations. And the last thing that we mentioned at the very beginning is that the reaction order is always defined in terms of the reactant concentrations, never for the product, right? We never see the product concentrations in the rate law expression is always with respect to the reactants.